A few things. I work at GE, but it's not a sales pitch. We'll try to keep it as vendor neutral as possible and very non-corporatish. Um, so, you know, ever since the dawn of humanity, people have been trying to see what is inside the human body. This is a picture of a gentleman called René Laennec in France, 1820, and he's trying to hear what's inside the chest of the person and detect tuberculosis. On his left arm, if you see, so in his left arm, you see that small little thing which is the first stethoscope. This person invented this stethoscope. And I just noticed today morning, I don't know whether this is a coincidence, that one of the elephants over here have something like that. I don't know whether that's a stethoscope or not. But that was 1820. And in 200 years, we've come quite a bit. And this is what we have now, a digital stethoscope. So, primarily all the data that we gather from inside the human body today is digital. That is the takeaway. And in this discussion, we shall talk about such kind of digital data that we can gather from the human body, the size of those data, and what are the challenges in handling and managing that kind of data at that scale. So I understand that a lot of people in this session are not from a medical imaging background, so I'll just take a few minutes to give you an overview of some of the things that we're going to talk about. It's a very basic super crash course in medical imaging. So in medical imaging, we have this term called modalities. And modalities are nothing but ways by which you can gather data from inside the human body and see that data in a visually, humanly interpretable form. So this is what we call a digital X-ray. It's something very similar to a normal analog X-ray, which many of us have had experiences with. You have a generator and an X-ray machine which kind of shoots X-ray onto the human patient who's lying down on the table. And you have a detector which sits underneath this, and it's kind of like the CCD detector that you have on your digital camera. It just captures an image which looks like that. That's what we call a side cut or a sagittal cut of the human spine. You can see a little bit of the skull and the mandible over there. Now this is one of the simplest forms of data gathering. This works on basic physics principles. You shoot X-ray, some of the X-ray is absorbed by the tissues, some of it is absorbed by the bones, some of it passes through. Okay. And this, what we need to remember, this is 2D. So you kind of see a 2D plane of what's inside the human body. Very good for finding out fractures, tuberculosis, that kind of stuff. This is another imaging modality called computed tomography or CT. This works on a very similar principle to that of an X-ray, but the difference is that this is in 3D. So what happens is, there is a rotating X-ray, which kind of goes around your body when you are lying on the table. And it gives you a shot from different angles, which you can all compose together and build up a 3D volume. And that's kind of what a 3D volume looks like with color maps and textures put on it. And then we have magnetic resonance imaging. Okay. What this does is it uses the properties of magnetic spin inside the human body. We have a lot of water molecules, and this uses the property of magnetic spin in these water molecules, and this is good for imaging tissues inside the body. It's not really very good for bones, but if you look over there, this is a picture of a ligament in your knee, which is not your knee. It's somebody's knee which is getting compressed by these two bones. And then we have another modality called the PET. It stands for positron emission tomography. This is very interesting. This does not really show you the structures in the human body per se. But what we do is we inject a radioactive biomarker inside the human body. And the biomarker has the property of latching on to cancer cells. And when it latches onto cancer cells, it starts emitting, it undergoes a positron decay and starts throwing out photon particles. And then you have this, you have a whole ring inside this which catches and counts these photon particles coming out of your body and understands that this is where the cancerous tissues are. And then we superimpose that on a CT image, which is very good at kind of showing the structures, the bones in the human body, and find out exactly where the problem is. So essentially the red areas that you see or the dark areas that you see over here, these are known as hotspots. So you can kind of find out if there is occurrence of cancer or, very importantly, a relapse of cancer in the human body. Many times we see a patient comes in for cancer treatment, goes back home completely cured. The cancer was probably somewhere in the shoulder, and 18 months later finds out that there's a relapse of a different kind of cancer in the ankle, in a completely unrelated body part. So PET scans are good. You scan the whole human body, 1.2, 1.3 meters of the human body, and you can find out if there are any cancerous cells anywhere that are malignant and growing. So the basic fundamental of imaging is this. This is what we call the basic image chain. You have the human body, and you have what's called a digital acquisition system, or an electromechanical software system which picks up signals from the human body. It can be a change of magnetic spin, which is conveyed by an RF frequency. It can be simple X-rays passing through the human body. It can be these photon counts which the digital acquisition system picks up. But essentially what we're trying to do is, there is a change in the physics inside the human body, and we are using some kind of a quote-unquote camera to catch that and get some information. Now, the information that's captured by this digital acquisition system is nothing that the human eye can understand or the human brain can understand. For example, photon counts coming from the human body. We will not be able to understand that. So we have something is done to these signals, and these signals are mostly they're not even in the visual XY or XYZ plane. They're not in a three-dimensional visual axis. So we construct an image from these signals, and that's a whole different ballgame. We're not going to do that, but essentially what I want to convey is we have some signals coming in from the human body, we construct images out of them, and then we add patient information. Obviously, when we are doing medical imaging, it does not make sense if there is no patient context. So we gather the patient context from either the database or the guy who's doing the scan types in the name of the patient, the age and weight. We add the patient context, and then it comes on a viewer, which finally humans are able to understand. They're able to look inside the human body and diagnose the problems. So the crux of this slide is, the fancier your digital acquisition system is, the larger your data set. It's kind of this similar principle as the number of millions of pixels that you have on your digital camera. The more the number of pixels, the bigger your raw file size is going to be. So let's get into how big is that image data really. This image data is broken up into two parts. One is the header information, which primarily has a bunch of information about the patient, who has referred the patient, what kind of a scan is it, what's the age of the patient, but primarily text data. And then we have pixels of information, which is actually an image that you can see visually on the computer screen. The text data hovers around a few k's. And the pixel data, assuming that it's a 1024 by 1024 image space, and these are mostly grayscale images, mostly. You have 16 bits per pixel, it works out to about 2 megabytes. So 2 megabytes of data. But that's not much, right? 2 megabytes is not really huge data. Why do we have a problem? The problem is that these data sets don't come along. you have a series of data sets that's acquired when you are doing a medical image scan. And each of these is around 2 megabytes, depending on the kind of scanner, the kind of modality. We're just talking orders of magnitude. So when you put a human on a table and you're scanning that person, you got a picture of these slices of bread. And that is exactly how it looks like when the images come in. It's as if you're cutting the person, you're creating slices of that person and looking into the person this way. This is the nature of most of the data that we have. So these data comes in volumes, or we have different medical terms for slices, some call it series, but essentially there's a large amount of medical data which comes in. And not only this, when you do a scan, we have multiple kinds of scan. I mean, if you want to do a CT scan, it's not just one set of data. CT scan will have 4 or 5 different sets of data based on the parameters which the doctor wants to apply on the data. So kind of multiplies very, very quickly. These are what we call slices, individual slices. This is a pictorial representation. So you kind of, if you cut off the head and you are looking from the top, this is what it would look like. So this is your gray matter. And so how big are these data sets? So if we'll take an example of a CT cardiac scan. If you look at a CT cardiac scan, you can have 3,000 images per set. And each of these data, so the size of one data set is about 6 GB. And for one exam, one person goes to the hospital one day, takes one exam, it can multiply up to 36 GB. So this is the size of the data that we're talking for one person. So then the question comes, how do we take it home? How many of you have seen an X-ray film? Some of you have. This is what it looks like. Okay. You go to the doctor gives you this X-ray film after taking the X-ray, or if it's a CT scan, he's going to compose a film like this, which looks pretty much like this, but he's going to put a small number of images, not you've got 2 images over here. He's going to put, like 10 by 15 stacks of images and give it to you. The problem is, this is not digital. Okay? You have to take it, you have to carry it home, you have to preserve it, and there's no way to keep this film safe for a long period of time. 10 years, 15 years, you cannot. Then obviously with advent of technology, what we have are what we call interchange media. It can be CDs, can be DVDs. So the doctor will burn all your digital data onto a CD or a DVD and give it to you. So you could take it to another physician and you can show it if that physician accepts the DVD. We have some format and protocol problems which we'll get into later. But the bigger question is a medical legal question. Who is responsible for preserving this data? What happens if this data gets lost? Today in India, the laws are not that strong, so we do not have good governance over medical data. In other parts of the world, particularly in Europe and US, the governance of medical data is strong, very strong, and it's getting stronger by the day. We'll get into that in a while. So fundamentally, if you want to store data and if you want to share that data, we need a format and a protocol. Think about JPEG files. If you want to send me JPEG files, you first have to have a format definition that your computer and my computer can understand. And then you have to have a protocol. It can be an HTTP-based protocol, you can have an FTP-based protocol, but there needs to be a certain protocol. The fun part about medical imaging is that up until 1993, there was no standard protocol in medical imaging. And that's a picture of the Tower of Babel. It's a biblical story which kind of goes on to say what happens if you don't have a standard way of communication. It's funny that the X-ray was invented in the early part of the last century, around 1920s. And for around 70 years, there was no format for capturing, storing, and sharing medical images. That changed. Around 1993, we started to work on a But generally, the community started working on a standard, and we've got a standard called DICOM. It stands for Digital Information and Communication in Medicine. So DICOM deals with primarily the kind of images I've shown you: the CTs, the MRs, the nucleomed cameras, ultrasound, X-ray, and now it's getting into the field of pathology. So if you have a digital microscope and you capture some data, you want to store that data, you want to share that data, we have this standard called DICOM. It's a pretty complex standard. It's huge. Actually, it's huge. It's kind of like what I see like the Indian Constitution. So there is a standard, but there is no standard way of interpreting that standard. Because when you have, every year there are 12 or 13 supplements to the standard coming out. So what your interpretation of the protocol is, or the data format is, may not be the same as my interpretation. And we get into a lot of problems with that while sharing images. So one thing which we need to know is that DICOM is based on TCP/IP, and this is very important because we are going to take a look at some of the problems that this offers. So this is kind of based on the TCP/IP protocol. When it started, and this is a historic slide, when it started, it was not even based on TCP/IP because TCP/IP itself was forming. So they had a physical 50-pin connector that you would run between two machines and use basically a data link kind of a protocol to transfer data from one machine to the other machine. So we'll get into a mind exercise on how much data do we really need to store these images. And what we're going to try to answer is how much disk space is needed if I'm going to do a cardiac screening of everyone in Bangalore. I want to do a CT cardiac scan to rule out the possibility of calcification in the human heart for everyone in Bangalore. How much data space do we need? This kind of thing is not exactly a mind exercise. There are communities, there are governments which are actually trying to do this for the health population. We don't have in Bangalore yet. Once we settle the CM Rao, we will look at that. But this is a very important question. How much data do you need? And that is the crux of the challenges and problems. Now, one thing what I want to say is that these are back of the envelope calculations. So worry about the magnitude of the scale, not the exact numbers. Because depending on what kind of a digital acquisition system you have, your size of the data could go up or go down. But the order of magnitude remains same. So this is the proposed route map for the Bangalore Metro. And this is the heart, this is the human heart. So assume that we have a population of 7 million people in Bangalore. Give or take a few, 1 million. And everybody is not going to be able to do a cardiac scan, and we do not need to do a CT cardiac scan for everybody in Bangalore. So let's take a cutoff percentage as 50%. Roughly people over the age of 35 or nearing 40 would want to do a scan, and we can debate whether it is 50% or 23% or 47%, doesn't change the numbers. So the hard disk space that's required to store a CT cardiac scan is around 20 gigabytes. That is for one person. So the space that we need is 70 petabytes for just the city of Bangalore. If we were to do a population health exercise, we would need 70 petabytes of data for the population of Bangalore. So how does it look in scale when we put it into perspective? 20 terabytes of data, that's the Library of Congress. Okay. AT&T call records, 312 terabytes of data. This is the largest single database in the world as of today. It's got a few trillion rows of data. Google Earth, and this is just the land part. We're not so much interested in the water part. The emerged land database for Google is close to 450 terabytes of data. And this is the Google crawler. This data is actually a few years old, so this could have changed, gone up by 100 terabytes or so. 850 to 900 terabytes is the size of the Google index, not the index, including all the documents. Then put 70 terabytes, 70 petabytes, it's kind of, if you would put that 70,000 terabytes, it's going to go through the ceiling. So that's the data space we need to do proper population health management, which we don't have. So we don't do proper population health management. So just to get you involved in some of these numbers, we actually have Christian Medical College in Vellore who are keeping track of all the scans that they do. They've been keeping track for the last 10 years. And their database size is around 60 terabytes. We have a healthcare, it's a group of 14 hospitals in Israel whose database size is growing at 20 terabytes annually. 250 terabytes annually. Vellore has 500,000 of exams per year. This entire hospital chain has 4.5 million of exams every year. The estimated imaging data size just in the United States in 2014 is around 100 petabytes. And estimated imaging size in 2020 is 35 zettabytes, which is like 10 to the power 6 petabytes. So it's a lot of space. So fundamentally, there are three challenges that we have in medical imaging. One is archival. How do we store the data? One is search. Now that we have stored the data, how do I retrieve the data from that huge database? If you go in for a doctor's consultation and the doctor wants to bring back your 5 years of medical history, including images, it needs to be done in a finite amount of time. You would not like to wait for like 5 hours for the images to come back. And the third is transfer. These huge images, this is one of the principal problems. How do we move these huge images from one place to the other place? And before this slide. So take this example. You write a blog post and you put it up on WordPress. It's a very important blog post. You don't have a local copy. You put it up on WordPress and 3 days later you find that the WordPress server has crashed, the database gone conked off, and your blog post is not retrievable. What is going to be your reaction? You're going to be mad. But more than being mad, is there anything that I can do as an individual user? Right? I can write another blog post on Blogspot saying how bad WordPress is. But there's not much we can do. This is not the same with medical images. Governments around the world regulate that anybody who's storing medical images provide a guarantee, like the hospitals or the clinics that are storing medical images, they provide a guarantee that these medical images are going to be preserved for a really long time. Let's take that. This is some data from the National Health Services in the UK. The British government rules that for mothers, you have to store data about the mom and the child for at least 25 years. So if you know anybody who's a pregnant mother, she has an ultrasound scan, that data needs to be stored for 25 years. If somebody's suffering from Alzheimer's, you need to store that data for at least 8 years, even after the patient has died. For children, when a child is born with a condition like a congenital heart or neonatal jaundice, you take some scans, you got to store until that child is 25. So this concept of providing guarantee, how do you do that? The good news is that the DICOM standard builds in a protocol called storage commitment, where there is a protocol by which when you send an image from one of these modalities or a CT scanner to the hospital image server, there's a protocol which guarantees that the image has been stored over there properly and you can delete the image from your local data store. Okay. Again, huge capacity requirements. This one is particularly interesting. Space and data center grade infrastructure. Storing 60 terabytes of data, which CMC Vellore is doing today, is not possible for every other clinic and hospital in India. And you are not going to get that kind of a storage guarantee or that set of hardware through which you can say, I'm going to be able to store this data for a long time. it costs a lot. It just costs an awful lot of money, and that's why these systems which guarantee storage service are extremely costly. The second problem is actually finding the data. Once you've stored this data, how do you find the data? And it turns out that search is actually a software problem. It's not a very complicated problem. The reason is at this point, we are not so much interested in the pixel data. The pixel data is so huge, we don't really know what to do with it. Even if we had a way of traversing through it, we don't know what to do with it. So what we do is we index only the metadata or the header information of patients. And the other part is that this standard called DICOM, because of the time it was built, it's a very structured schema-based standard and loves SQL. Okay? You can even see concepts from SQL which has been taken into the standard. So all you need to do is store your header information into SQL tables. And the pixel information is stored in flat files. Now this is a pattern. This is something that we at GE Healthcare do across a large number of our product lines, and over the years we found it to be very useful in our situation. Does not mean that this is a standard way of doing it. There are organizations which will insert this pixel data into a blob object, into the SQL table, which kills performance. But this is something that we do. The good thing is that you get the power of SQL queries when you are looking into your database. I want to look at Shaurya Sarkar's CT scans from 1st January 2000 to 31st December 2005. It's a very simple query. The database is huge, but that's what databases are meant for. They give you the power to find that data very quickly. Insertion is fast, and reading is also fast because we use memory mapped I/O, because the pixel data is being put into flat files. So you can really read and write very quickly from the disk. We use something called table replication because it's very common for a database to crash while a system is in operation. So while a database is in operation. So yesterday I happened to go to CMC Vellore, and they were saying that even with their power backup, they see a lot of power cuts, which means that their database just goes boom. Okay? Even with the UPS, it barely serves the purpose. So we do see a lot of database crashes, but we replicate just the tables, not the flat files. And the best part of it is that since we stored the complete file as a flat file, it is possible to recreate the header data from your flat file. So the next question is transferring these data. The fundamental question is, why would I want to transfer the data? Turns out that there are three reasons, and I'll kind of skip between the next slide and this one. So this is what happens in a hospital really. You've got these modalities, a CT scanner, an X-ray system, an MRI scanner, which are continuously taking in images. Patients are coming in, coming out. Just a hospital like Vellore does 1,005 acceptable for medical image. DICOM does not tell you anything about what is acceptable or what is not acceptable. But what DICOM does is it gives you the standard for using JPEG 2000 as compression engines for these images. And what kind of a quality factor you build into those JPEGs is a choice that you have to make. And you have to clinically validate your product before selling it in certain parts of the world. For example, if you were to make a viewer which has like a QF of 30, and you have to prove that 30 is valid for human imaging in, let's say, USA. So there's a clinical validation which needs to happen. Good question.
And what about noise, handling noise in the data? So for example, you have taken an image and you are sharing it with others. So is there some kind of signature mechanism taken at the beginning that makes sure that data is still intact while it has been transferred?
Are you talking about checksums or are you talking about noise?
Something of the kind of checksums actually. So while transferring data, it's really highly likely that the data gets corrupt, and the person sitting on the other side could still be able to see some images, but how can we be sure that there's no noise in it?
Great question. DICOM provides you a basic checksum feature. It's not a very advanced checksum feature. So you can, more than checksums, you can have a threat of somebody entering into the system and actually manipulating your data. But since these data sets are complex and there's not a lot to be gained, this is not financial transaction data, we don't see that kind of attacks on a DICOM stream.
So I didn't mean attacks, whether, noise being introduced due to some environmental.
Yeah, so DICOM provides you a basic checksum correction, but it's not like an MD5 that is guaranteed.